Hi students, this is lecture 1 for the network simulation course. In this lecture we are going to talk about basic concepts of network model definition. First of all, before understanding what is network simulation, we have to know what is simulation and why is simulation important. Why simulation is important? Simulation is the imitation, mocking of a real-world system through a computational reenactment of its behavior. It means mimicking its behavior according to the rules described in a mathematical model. So to have a simulation, we should have a mathematical model, and we will imitate the system itself by its behavior. This is all about simulation. The act of simulating a system generally entails considering a limited number of key characteristics and behaviors within the physical or abstract system of interest, which is otherwise infinitely complex and detailed. Any system is complex and it can be bounded. It's infinite complexity. But when we deal with simulating, we can't do everything, or we can't cover all the behaviors of the system. We will choose, or we will simulate things that are important and that are useful for us. Simulation allows us to examine the system's behavior under different scenarios. For example, if you are going to make a machine or some product, you have to test it for different scenarios, even if these scenarios are not possible in the real world, but just for making sure. This means that which are assessed by reenactment within a virtual computational world. For example, if you want to test your product, how much temperature it can tolerate. So you can, if you are going to test your product for high temperature, you can put your product in an oven, for example, and raise the temperature for its maximum limit, and see what's your system's behavior will be, what's your product's behavior will be. If you are going to test your product for the low temperature conditions, you can put it in a freezer and test if this product can tolerate low temperatures. But usually simulation occurs in this is not a simulation, this is the original condition based. Usually simulation is done using computers by using the equation itself. Okay, simulation can be used to identify bottlenecks in a process, provide a safe and relatively cheaper in terms of both cost and time. Test bed is actually a very important term in network simulation. When you are going to test anything, you have to have a test bed for it. Is to evaluate the side effects and optimize the performance of the system, all before realizing this system in the physical world. So before you put your product or your system in the physical world, you have to pass very many evaluations of using simulation. So why is simulation is important? Simulation is important because it will give you a safe and relatively cheaper than the original test bed. If you do it by using computer, for example, you can also evaluate the side effect and optimize the performance of the system. We will discuss these later on more thoroughly. But for an example, why it's much cheaper to do things in simulation rather than in real world? For example, if you have a company that designs jet plane, and when they made based on the calculations of how the jet plane will fly, and what the average fuel consumption will be for the jet plane, you have to have a simulation for that. You can't test the airplane just after finishing making it in the industry. Suppose that there's a simple mistake in the design, you will lose the whole jet plane, you will lose many all your effort, and you have to build the plane from zero just for a single mistake. So simulations can be used instead of testing the real plane in the sky, for example, and this will have a relatively cheaper and safer to do so. So simulation, not just in network, in everything, is very important, and you have to learn its basics. And you may in the future use simulation a lot in many different aspects of your engineering world. Here are some important simulation examples. We have here weather simulation. You all know sometimes in weather they predict there will be a storm or a tornado or a hurricane coming to some city or something thinking. They simulate the tornado or the hurricane before it reaches the coastline of a country, for example, 5 to 4 days ahead. This is very important, just to tell the people, residents, these areas, regions, to take care and to embrace the risks of this storm that's coming to them in the near future. They use special computer systems and satellite information to deal with weather simulation. Here's another example of flight simulation. Usually pilots, they are not trained in real planes actually, until they pass the flight simulation itself. These systems are very expensive and very accurate. It's just like you are going to fly in a real plane. And these systems are very important as well, because it will provide you a cheaper method for training your pilots instead of risking your plane at the hand of the pilot who doesn't know anything how to deal with an airplane on in his or her first training. Okay, let's jump to a model. What is model? We have many models. Let's start with a computer model. A computer model is a computer program that attempts to simulate an abstract model of a particular system. Computer models can be classified according to several orthogonal binary criteria, including: when dealing with a computer model, we have many states we have to discuss. There are many two states, continuous state and discrete states. You may know about these states from other subjects in your study. If the state variable of the system can assume any value, then this system can be modeled as continuous state model. These variables that can have any value, then the state is continuous. On the other hand, a model in which the state variables can assume only discrete values, not any value, only a specific number of values, it's bounded values, is called a discrete state model. Discrete state models can be continuous or discrete time models. This is a little bit tricky, but don't confuse it with the continuous here. Continuous values does not mean that the values are any value. Even discrete values can be continuous state, or discrete time models. This is time dependent. You have to make a distinction between a state and time. Continuous time models, discrete time models, sorry. If the state variables of the system can change their values at any instant time in time, then the system can be modeled by a continuous time model. This means that the value is changing in any time. Let's say it's like, for example, if you are dealing with a system that changes the value each second, this is a discrete time model. But it changes value like for any given time, and you can't predict what time it's going to change, then it's a continuous time. Just like analog system and digital system. Analog system, they change their value at any instant time. Then the system can be modeled by a continuous system. On the other hand, a model which states variables can change their values only at discrete instance of time is called discrete time model. These basic terminologies is you already know about from other subjects, just like you're going to state it in DSP. I'm not sure if you have already studied it or not. I think you have studied signal systems, and these terms are very important in signal systems. Here are examples how to differentiate between continuous and discrete system. Look, in discrete systems, there is a specific amount you can predict how much the system is growing, for example. While for continuous growth, it can be expressed by a function, and it can take any value. But here it is like 1, 2, 4, 8 only. And for continuous and discrete data, look, we have several examples here. It's any value. You can measure any value. Specific values, you can count it. For example, here you can count the number 2, but here you have to measure it by making a coordinates for the x-axis and y-axis, and to find out what's the value here. You can measure it. For example, you have measured it is like 56.2 or sorry 5.6 or 2.4989, while for the discrete data is 1, 2, 3, 4, 5, 6, etc. Any value can be temperature, can be any value at any time. For example, here specific data is like number of students or number of cats. We have here a special type simulation. They call it agent-based simulation. This simulation is a specific type of discrete simulation that does not rely on a model with an underlying equation. So it means that it has unknown equation, but can nonetheless be represented formally. You can present it as an agent-based simulation, or you can't predict what's going on, but you have to know the information from the behavior of the system. In agent-based simulation, the individual entities such as molecules, trees, humans, consumers, cells in the model are represented directly, rather than by their density or concentration. As we discussed previously in the simulation, we said that simulation we are not going to cover all the system behavior to simulate it. Here in agent-based simulation, you can't take like some behavior of the system of the entities. You have to represent it directly. Like if you are testing a human, you will test on a human. If you are testing on animals, you have. This is very important in medical and chemical, and even in economics type of simulations. And possess an internal state and set of behaviors or rules which determine how the agent's state is updated from one time step to the next. Here are some examples. Like, look, in the real world, we have these people. The agent-based model, you will take these people exactly the same and test on them. Without, for example, here is like, it's like their face is not important in this type of simulation, so you are going to mark them as entities by their names or IDs or so example. This simulation environment is based on agent-based simulation or COVID-19, a contagious disease that is spreading all over the world right now, and how it affects the economical effect of people. Sometimes you say, okay, COVID-19 is a sickness or is a pandemic. What's the relationship of this virus or this disease to economical for other people? It's indirect, but it can be represented. So look at here, as an agent-based simulation, you will say, like, you will keep track of data of, for example, here, poor people, working class, rich, and so on, and you will affect their economies, their wealth is decreasing or increasing by the number of days is the virus is spreading, for example. This is just an example of what do we mean by agent-based simulation and why it's different than other types of simulations. Okay, let's jump to simulation models. We have now deterministic or probabilistic. In a deterministic model, repetition of the same input will always yield the same output. Okay, just like if you put x equals 0, then y will equal 1. Whenever you put x equals 0, then y will equal 1, for example, for a function or specific function or something. On the other hand, if in the probabilistic model, the repetition of the same input may lead to different outputs. It's based on probability. Probabilistic models use like random number generators. This is very important, and we will discuss later how to generate random numbers, other than assignment, of course, to model the chance or random events. They are also called Monte Carlo simulations. We will discuss that in the third lecture or in the fourth lecture, how we can manage to do Monte Carlo simulations. There are a special type of models, they call chaotic models. They are new, constitute of a special case of deterministic or continuous state models, deterministic continuous state models, in which the output is extremely sensitive to input values. Chaotic models they are not random models, but its behavior change, like it's very sensitive to the input values. If you change very tiny thing in the input, the whole output will be different, a complete different world. We have here linear and nonlinear models. If the output of the model are linearly related to the input, then the model is called linear model. You know that. However, if the outputs are not linear functions of the inputs, then the model called nonlinear model. Here are some examples of probabilistic data and deterministic data. For example, in probabilistic, you only can see the shadowed half of the person. So, for example, his gender, he might be male. It's not certain. For deterministic, its data is already written or taken from the person himself. Look at the other description, so you can easily find out what is the probabilistic and deterministic data. Here is the example between linear relationship and nonlinear equation. In nonlinear equation, it's the input is not directly proportional to the output. Or in the linear, no, it's you can predict. Like for example, if the input is like x, based on the linear equation, is linearly dependent. But for nonlinear systems, it's not equispaced proportional. Here's an example of a chaotic equation. It has many equations. So this is an example of Lorentz equation, and have these type of like a butterfly shape equations. We may discuss these types of systems later in assignments. Let's talk about stable and unstable models. If the dynamic behavior of the model comes with a steady state with time, then the model is called stable. Models that do not come to a steady state means that the future values is not coming to a steady state within the time, they call unstable system. We usually prefer, or engineers prefer, to make the systems stable. Note that stability refers to time, while the notion of chaos is related on the behavioral sensitivities and the input parameters. Okay, here is the difference between the chaotic systems are related to their input, so they are not unstable. Unstable systems, as the input change, the system is going to nowhere, no specific direction. Local or distributed, this is an example how we can name or tell if the simulation is executing on single computer or a network of interconnected computers. There are some examples of distributed simulation. There are several elementary standards. Distributed simulation include aggregate level simulation protocol, distributed interactive simulation, DIS, and high level architecture. Here are some examples of stability. If we have this input, fixed input, look, for a specific system, this output is stable. Why it's stable? Because at the end, as time passes, it's going to resonate about fixed value. So you can expect in the future its value. This system is called stable system. There's another system here. It's like as you go by time, the system is predictable. It will reach a specific value. This is another type of stable system. In this system, we have a marginally stable system. Why it's marginally stable system? Okay, because the cycle repeats itself with the time. It's not going to a specific value, but you can say that the system is predictable. There is nothing unknown going on in the system. As examples of unstable system, these two kinds of systems are unstable. Why? Because there is no specific value we can predict in the future. It's like by the time is going, the system is unknown. It's going to nowhere. Just like this one. It's just expanding while the system. An example for an unstable system, we all know when there's if you put a microphone in the front of a speaker or amplifier, and this annoying sound will appear like that and increase itself until the system reaches limits or something. This system is becoming unstable. Why? Because the input is amplified itself all over again, and the system becomes unstoppable. Sometimes when we discuss how to make system stable or not, we usually, to make a system stable, we have to draw a curve or like local minima for the system. This ball, specific ball, it will be stable if you put it in a valley, and the value eventually it will go to the lowest points of the valley. But if you put a ball on this top of a hill, you can't expect what's going on, left or right, and it's not going to be stable.